And then discussing some of the descriptive measures. The very reliable and the most preferred measure is the standard deviation. Here you see the standard deviation. And then we have range. It's a crude type of a measure because it's the difference between maximum and minimum value. It account for two extremes only. It discuss only minimum and maximum values. That's why we consider such type of a dispersion measure as a crude measure. And it contains 100% of the data. It actually provide us the length within which 100% of the data is lying. And then talking about the interquartile range, as I explained earlier, the interquartile range is the difference between lower and upper quartiles. So what these quartiles are, if we make a data array, means arrange our data from smallest to the largest value, and we divide it in 4 equal parts. Each dividing point is quartile. So the first quartile covers 25% of the data, and after the first quartile, 75% of the data values are lying. And next to it, the dividing point is the median. The median is the point which divides the data into equal parts. The 50% of the data is below it, the 50% of the data is above it. And the quartile next to it, or the dividing point next to the median, is quartile number 3. And before the quartile number 3, 75% of the data observations are lying, and after the quartile number 3, only 25%. So it means interquartile range is the difference between Q1 and Q3. So since it contained 50% of the data, leaving the 25% data on the lower end and the upper end. So it accounts for the 50%, middle 50% of the data. And interquartile range is preferred in case our data are non-normal. And otherwise, if your data are normal, you can take any of the dispersion measures. They all would be equally good. But in case your data are non-normal, we should be very particular in selecting the appropriate average and appropriate dispersion measure. We usually prefer median in case your data are non-normal, and for your dispersion measures, we prefer interquartile range in case our data are non-normal. And now question is how we can judge whether our data are normal or not normal. To determine this fact, we have two measures here. One is skewness and the kurtosis. Skewness, as I explained earlier, that skewness is lack of symmetry. Means if your data has longer tail to the left side or the right hand side, that is no more symmetrical, and we call such type of data skewed. And there are two types of skew: as a positive skew, the negative skew. Positive skew means a longer tail to the right hand side, and the negative sign is indicating the negative skew, means the longer tail to the left hand side. So you see here, our skewness statistic is 0.116. 0.116 is positive, so you can say here our data is a positive skew. And similarly, if you check with the kurtosis is a negative kurtosis. Kurtosis actually explain about the tails of the distribution, because in the normal distribution, skewness is 0 and kurtosis is 0. For normal distribution, both of these statistics are 0. And in case our kurtosis is negative, it means that your tails of the distributions are not compatible with the normal distributions. As these values gets larger and larger, it means the factor or the element of skewness become intense. How we can judge whether the skewness is dangerous for the data means you can say this there is a significant skewness and significant type of the kurtosis. These are both, either of them are dangerous for the normality of the data. And you can judge it by calculating the z-score of the skewness. And how we can calculate the z-score of the skewness? If you divide this statistic by the standard error, that would be called the z-score of the skewness. And similarly, if you divide this kurtosis statistic to its standard error, that will be the z-score of the kurtosis. And if the z-score of the skewness is greater than 2.5, you can say there is a significant skewness in the data, and that skewness is significant, and the related data cannot be a normally distributed data. And similarly, you see here, if you divide this kurtosis statistic to standard error, that would be the z-score of the kurtosis. And if this z-score of the kurtosis is greater than 2.5, it means there's a significant kurtosis. And in this situation, the data cannot be normally distributed because of the significant kurtosis. And now discussing what would be the effect of this negative sign or the positive sign with the kurtosis. If the kurtosis is negative, it means that our height of the curve is a bit higher than the standard normal. And in case your kurtosis is negative, it means your distribution is flatter than standard normal curve. And if it's positive indicate that your peak of the curve is a bit higher than the standard normal curve. So that's how we determine whether your distribution of the data follow the normal or not. So keep in mind that for the data to be distributed normally, neither of skewness or kurtosis should be significant. I repeat that in case significant skewness is there or significant kurtosis is there, such data cannot follow normal distribution. And how we can check whether the skewness is significant? That is, you divide the statistic to its standard error. In case that ratio is greater than 2.5, ignoring the negative sign, we can say that skewness is significant. And similarly, if your skewness statistic divided by standard error, ignoring the negative sign, is greater than 2.5, your kurtosis would be significant. And if either of these two, skewness or kurtosis, are significant, your data cannot be distributed normally. So that's how we judge whether this sample can be from a normal distribution or cannot be from a normal distribution. So in this particular situation, considering the yield number 4, if you divide this 0.116 to 0.564, that result is very small and it's too small, so you can say your skewness is not significant, or you can say your data is approximately symmetrical. And similarly, if you divide this kurtosis statistic to its standard error, this ratio is hardly 1.3, and that is not greater than 2.5, ignoring the negative sign. So you can see there is no kurtosis in the data. So you see, significant, neither the skewness is significant nor the kurtosis is significant. So we can say that the yield number 4 sample is coming from a normally distributed population. So similarly, for the yield number 8, if you divide this skewness statistic to its standard error, the answer is less than 1. And similarly, for the kurtosis, if you divide this value to its standard error, that result is also less than 1, ignoring the negative sign. As you see here, neither skewness is significant nor the kurtosis is significant. So the yield number 8 is also coming from a normally distributed population. So here, the descriptive analysis of the yield number 4 and yield number 8, we determine that yield number 4 follow normal distribution as well as yield number 8 also follow normal distributions.